Okay, it's time to begin Unit 17A, Sound. And the place to start is, how do we classify sounds? Usually it's by frequency. All of them sounds are, air compressing and rarefying, compressing and rarefying is going along, this kind of thing. But the air molecules, rather than the spring, it's all going from here to there. I can make it go backwards if I spin one that way. That's all it is, traveling, but the air molecules do this, it travels along. Of course, it spreads out too in the air, unlike on the spring where it has nowhere to go but down the spring. If it's doing this really quickly, so we can't hear it, we call it ultrasound, ultrasonic, above the sound. Insects often create and hear sounds up here. That's why if you have really good hearing and you go into some stores, you hear this really high-pitched sound, well, that's there to scare the insects away. It also does a job on dogs. Then we have the audible range. That's about 20 hertz to 20 kilohertz. 20 kilohertz if you're young anyway. If you get older, that sort of drops down to maybe 15 kilohertz, even less if you get above that. On the low side, some people can hear down to about 12 hertz, and that's the frequency your blood flows at. You get this little low sort of crunching, squishing sound as your blood flowing. Some people can hear that. Infrasonic is below, you can hear it, so below 20 hertz, and you get atmospheric resonances and things going on there. And yes, the atmosphere actually does bounce. It's a spring, air spring. And if you've got, say, one of these tsunami waves, it sort of gets pushed up because the Earth's crust pushes up in a earthquake, then that motion transmits up. It's a very low frequency all the way through the atmosphere, and then you even get a breaking of the wave, like get breaking of ocean waves high up in the atmosphere as it gets to too low a density, and it becomes really big variations. That actually heats the mesosphere. Biggest reason for heating of the mesosphere, in case you're worried about that, that's the middle atmosphere, way up high on the stratosphere and above. So they're there, but we can't hear them. Most things like your computer are going to filter out anything outside this 20 hertz, 20 kilohertz range because you're not supposed to hear it anyway. So that's the classifications by frequency, and we'll stick with frequency for a little while, and then we'll move on to the other properties of sound, like it has signal strength, its amplitude, its power. Okay, so middle C on a piano is struck and produces a sound wave at 261.6 hertz at 0 degrees F. What is the frequency of the sound wave if air temperature is increased? Well, the short answer to this question is change in temperature is a medium effect. Frequency is determined by the source. Right, so medium check means it affects the velocity. So the frequency here is determined by the source. And so delta T doesn't change. Change the frequency, and 261 goes to 261. That's done. But while we're here, what effect does this actually have on the temperature? And so, let's say answer, say, part 2 here. if the, let's see, do I have a part 2? Oh, I have a part 2 right there. Maybe I should just go ahead and do it on part 2. So, of course, I should note here, lambda does change because lambda is equal to v over the frequency. So that doesn't change by source, changes. And so that change here propagates, blue yet on this page, this change propagates right into there. Okay, so now 2, the speed of the sound wave is 331 meters per second, so 0 degrees. What is it at 20 C? And so we write down our rule, air at atmospheric pressure. You have V is equal to 331 meters per second times the square root of T over 273 Kelvin. And a few notes here. Kelvin is absolute temperature. That means it's 0 K is, that's not OK, that's 0 K. K is the unit. That's the number. Is when there's no energy, no thermal energy. And of course, T in degrees C, which has a degrees sign there, is equal to T in Kelvin, which has no degrees, minus 273.15. We're neglecting the 0.15 here. And it goes the other way. If you add this to both sides, you get the, how to get Kelvin. So 0 degrees C, which is what we have here, goes to 273 Kelvin. And so our V at 0 degrees C is equal to 331 meters per second. The square root of 273 over 273 is equal to 331 meters per second. That's what it says. And V at 20 degrees C is equal to 331 meters per second. The square root of 273 plus 20, that's 293 over 273. And that turns out to be the 331 meters per second, the square root of 293 over 273, and that's equal to 343 meters per second. I can also ask, what are the wavelengths? And so let's do those. Lambda at 0 degrees C is equal to 331 meters per second. It's V divided by the frequency, 261.6 cycles per second. That's hertz. And that's equal to 1.26 meters. I'm going to put it in black because we usually drop it. And if we go lambda at 20 degrees C, that's equal to the 343 meters per second we just calculated, divided by the 261.6 cycles per second. And that, if you work it out, is 1.31 meters. And then, of course, I'll put the cycle in black here. and the per cycle is usually dropped. Even though it is there, it's still usually dropped. I think unfortunately, but you know, some people like that. The key thing that we're using here, of course, is V is equal to lambda F, or lambda is equal to V over F. That's our go-to equation. That's what shows up here, and that's what we're using. Okay, so that's probably about everything I've got here for equation part 17A. It's really just talking about the speed of sound. Once you have this equation and understand what Kelvin is, you can put it in there. Go back to our go-to equation if you need to pull these things out. And that is, and remember that what is the medium? What sets the frequency? And that tells you to answer all these qualitative questions like this one. Okay, that's all for 17A, and I'll come back to you next time with 17B.